announcements.
Good morning, Shop. Please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Now the Texas Pledge. Honor the Texas flag. I pledge allegiance to thee, Texas, one state, under God, one and indivisible. Now for a moment of silence. Teachers, please take attendance now. A message from Healthy Shafts. Before making a big decision, get educated on your options. This will make the choice easier and improve your chances of success. The Capstone Research class asks that you check your school email. Please take a few minutes out of your day to participate in any Capstone Research surveys you receive. The data collected is part of a grade for these students. Local scholarships are available through 2 different online sources. Requirements may differ between scholarships. Most require an essay. Please follow the prompts for the online local scholarship application and Austin Community Foundation application. All local scholarship applications are due by 5 p.m. on Monday, March 29th this year. And weekend news include host of Be the Match fundraiser at Chipotle is scheduled for this Saturday, February 27th. The final deadline to submit to the final draft is Sunday, the 28th. And Student Council is hosting a movie night at the PAC February 28th, this Sunday, from 7 to 9 p.m. You can purchase tickets at movies.westlakestudio.com. Have a lovely weekend, chaps.
All right, guys, you have a problem set due today, and then there's one next week. If you start next week's, before I get a chance, I keep forgetting to change it, the problem set for next week has 3 lessons on it, even though I cut one. So right now, the one in Google Classroom says 17, 18, and 19, and it should just be 17 and 18. I'll try and remember to cut that soon, but I keep forgetting to do that. So if you do start it, just know that the 19 one will be pushed till later, a later problem set, and it's not on this one. It's not on this test because I couldn't fit it in. So today we're doing properties of determinants. And we've only really seen determinants with a 2x2 matrix while we are trying to find an inverse. So today we're going to kind of go over how you would start to find them for other size matrices. They have obviously a lot to do with the inverse because we use it to find the inverse, but they actually tell us a lot of other things about our matrix. So we have a shortcut for our 2x2s. The determinant of a 2x2 matrix, you just multiply across and subtract. So we do AD minus BC. Okay, which is something we then use to find the inverse of those 2x2 matrices. If your determinant is 0, the matrix is called singular, meaning it does not have an inverse. Okay, this tells us things like there are dependent rows in my matrix. There are free variables. There are non-zero solutions to AX equals 0. R does not equal M equals N. The R is not the same as M or N. So some B's will have solutions, some will not. B's that do have solutions will have infinitely many solutions. All that stuff comes, you can tell by seeing the determinant is 0. Okay, all that stuff is from the same place. If the determinant is not 0, you have the opposite. There are no free variables. There are no rows that are dependent. AX equals 0 only when X is 0. The column space spans all of our N. Every B has exactly one solution. Okay, all that stuff is related, and we can tell that from the determinant. I'll list that one, all that stuff at the end if you wanted to see that. Notation-wise, this matrix A, if you want to talk about the determinant, you can either say the determinant of A, the determinant, and put the matrix there, or you can use straight bars instead of brackets. Make sure that if you see a determinant in calculations, that's a scalar. It's a number. It is not a matrix. So if I'm multiplying the determinant of A by something, you're literally, it's normal multiplication like you learn in first grade or second grade or whatever. It's normal multiplication, not matrix multiplication. So even though, especially with these two, you see that and you think you're seeing a matrix, those are not matrices. That's the determinant of a matrix. It's like the magnitude of a vector is not a vector anymore. It's a number. So determinant will be a scalar. So if I'm ever using it in any sort of arithmetic or whatever, it's just a normal number that you can add or multiply or whatever. Okay, and since we have that 2x2 shortcut, most of the examples that we'll do will be a 2x2 just so you can kind of see. But we're going to use this to then apply to larger ones, probably like 3x3s or maybe even a 4x4s or something. But all of these properties that we're going to go over today, there's 10 different properties that we'll look at. They all apply to all square matrices, okay, not just 2x2s, even though a lot of our kind of examples will be that, just to show a quick example. But they apply to all squares. Determinants only exist for square matrices, just like an inverse. If it's a rectangle, it doesn't have a determinant. All right, first property is the determinant is a linear function of any row. The textbook I use for some reason says the first row, but it's really any row. Which means if I take a row and I multiply it by something, your determinant will be multiplied by that same thing. So like if I had A and it was A, B, C, D, and my determinant was AD minus BC. If I took the first or second row and I multiplied by something, so I had AT and BT, and I find the determinant, I'll get ATD minus BTC. That's just T times the other determinant. Right? Multiplying row 1 by T, multiply the determinant by T as well. If I did row 2, it would have done the same thing. If I multiply 1 and 2, it'll multiply the determinant by both of the numbers. So I took row 1 and I multiplied by 2, and I took row 2 and I multiplied by 5. It would take the determinant and multiply it by 2 and then by 5. So each time you multiply a row, you'll multiply it'll change the determinant by that same factor. The other thing that comes from this, the determinant being a linear function of the rows, is if I add rows, determinants will be added too. And this is a little bit weird. And again, this is determinants, not matrices. So say I have two matrices with one row that's the same and one row that's not. If I find their determinants and I add them together, it'll be the same as if I had added that first row and then found the determinant. Okay, notice the rows that are the same, you leave them the same. It'd just be any single row. I could take those numbers and add, and we'll actually usually go the other way. You'll take something more complicated and you could break it up into smaller, easier to deal with pieces. So I could pick any row and start kind of subtracting out parts and breaking them apart. So I'll give you a quick example on the next page, but that's another thing that comes from it being a linear function of any single row. Okay, so again, this is not matrix multiplication, this is numbers. We're just gonna add these numbers. So for example, if I had a matrix 1, 2, 3, 0, 1, 0, and 0, 0, 1, I would notice that's very similar to an identity, right? Two of the rows are the rows of the identity matrix. The first row is a little bit different. It's if I took that plus 0, 2, 3, 0, 1, 0, 0, 0, 1. Okay, the two rows that are the same, I would leave the same. But this first row, 1, 2, 3, is 1, 0, 0 plus 0, 2, 3. So those determinants should be the same. As long as I only do it to one row. This will be nice because one of our properties will be that the identity has a determinant of 1. And one of our properties will be the determinant of anything with a column of zeros has a determinant of 0, which means this one has a determinant of 1 plus 0, which is also 1, even though it's not an identity and it doesn't have any columns of zeros. So we'll be able to kind of use this to break things apart and do it in little simpler pieces. Okay, second one, the determinant changes signs if you exchange rows. So again, we could show this really easily with a 2x2. This is AD minus BC. If we exchange the rows, we'll get BC minus AD, which is the negative of what we got the first time. So if we see something that looks like the identity with just the rows mixed up, I could start switching the rows back and just notice that every time I switch rows, it'll change the sign. So if I switch one pair, it'll change it once. If I switch two pairs, it'll change it twice, meaning it'll go back to the original sign. If I switch 3 pairs of rows, it'll change the signs 3 times, which means it'll be a negative of a negative of a negative. And so every time you switch rows, it'll change the signs. And sometimes this helps us kind of take one that maybe a mixed up one of something we could find a determinant very easy. You could kind of unmix the rows by just exchanging them. But just know that every time you do, you'll change the sign of the determinant. Okay, 3, the determinant of the identity of any size is always going to be 1. So like you could use these first 3 to find the determinant of like one of our permutation matrices. Right? I would say, well, that's really close to the identity. Switch these signs. I mean, these rows, sorry. It will switch the sign. That's the identity. So the determinant will be -1. Since I switched one pair of rows to get to the identity, this has the same determinant with just the sign switched. If I had had to switch 2 sets of rows, it would have gone back to positive. Okay, so we can start to kind of pair up these properties to take something that is unfamiliar and I don't know the determinant of and find its determinant. Okay, if 2 rows are equal, the determinant of the matrix will be 0. Again, this will kind of make sense because if the determinant is 0, it means that your elimination will give you a row of zeros, that you have dependent rows, that you have free variables, all that stuff. So if you have 2 sets of equal rows, when I do elimination, one of those is going to go to 0, which is going to give you a determinant of 0. Okay, these are all very interconnected, which means like you could prove it using the first couple properties that we did. So if I have A, B, C, D, E, F, A, B, C, that should be equal to the negative of A, B, C, D, E, F, A, B, C. Because one of our properties said if I switch rows, so say I switched row 1 and row 3, that should switch the sign of the determinant. Well, notice those are the same determinants, but with different signs. If they're equal, the only number that they could possibly be is 0. Right? If I take a row that's the same and I switch it, and it's supposed to switch the sign, but I get the same thing, I must have had a determinant of 0. Okay, or again, you could do a 2x2 and give that example as well. That'll be AB minus AB, which is 0. So anytime you see 2 rows that are the same, you'll get a determinant that's 0. This will be a big one for us. Subtracting a multiple of one row from another leaves the determinant unchanged. So when we do elimination, basically, it won't change the determinant as long as you are just subtracting a multiple of one row from another. So you know, if I have A, B, C, D, and I take row 2 and I add to row 1. In row 2, I'll have C plus 2A and D plus 2B. If I went and found the determinant of that, I'll have AD plus 2AB minus BC plus 2AB. Distribute the negative and you'll lose that 2AB and you'll end up with AD minus BC, which was the same as the original. Just be careful if you, sometimes when we've done elimination, we've taken like something times row 2 plus something times row 1. That will change the determinant. Look back at property 1. If I multiply row 2 by 2 and then add, I'll multiply the determinant by 2. I'll have changed it. But if all I'm doing is taking one of the rows and adding a multiple of another, nothing will change. Okay, but if I start doing like 5 row 2 plus 2 row 1, the determinant will be 5 times as large as the original. It will change it. Okay, a matrix with a row of zeros will also have a determinant of 0. We could show this using rules for properties 4 and 5. All right, if I take AB 0, 0, and I take row 2 and add row 1, it shouldn't change anything. But that gives me AB, AB. Which rule 4 said if I have 2 rows that are the same, the determinant will be 0. So that one should be 0, which means AB 0, 0 should also be 0, because it shouldn't have changed when I added 2 rows together. But again, when I see a row of zeros, there are free variables. There are infinitely many solutions to AX equals 0. There are R does not equal M and R does not equal N and all that stuff. That's the same as saying the determinant is 0. Okay, those are connected ideas. All right, this is another one that's really useful, especially when you pair it up to rule 5. If A is triangular, whether upper or lower, the determinant is just the product of the diagonals. So if I have a matrix like this, the determinant will be A times D times F. Which means if I have some matrix, I want to find its determinant, I could do elimination until that is triangular, multiply the diagonals, and then you've got the determinant. As long as to do elimination, all you did was take rows and add other rows, add multiples of other rows. If you do any row exchanges to get there, that'll change the sign each time you do it. If you multiply a row by something to get there, that will have multiplied the determinant by that same amount. So you'd have to kind of keep track of that. But otherwise, this is how I would find most determinants, is I would do elimination and then just multiply the diagonal entries. Okay, number 8, I've already said, if A is singular, the determinant is 0. Meaning if A has no inverse, the determinant is 0. If A does have an inverse, the determinant is not 0. Okay, if A is singular, that tells me U has rows of zeros. There are free variables. R does not equal M and R does not equal N. AX equals 0 has non-zero solutions, or the null space has non-zero vectors in it. Same thing. Okay, if we find the null space, there are other types of vectors in there. It means there are solutions for some B's. But not others. That situation is what we've seen in most of our problems because that's the more interesting one mathematically to solve. That's where we had like homogeneous solutions and a particular solution. You put them together, you have a complete solution. That was when you'd have something like this. You'd end up with free variables and all that stuff. If the inverse does exist, meaning the determinant is not zero, U has no rows of zero. There are no free variables. R does equal M equals N. AX equals 0, only when X is 0. The null space is 0 dimensional. There's exactly one solution for every B. Okay, all that type of stuff. You can tell that from the determinant. Determinant is 0. You will have either infinitely many or no solutions, depending on what B is. Determinant is not 0. You will have exactly one solution for every single B. There's an inverse, all that stuff. Okay, those are all basically related ideas. Okay, remember that we're only talking about square matrices here. If it's a rectangle, determinant doesn't really tell you this stuff. But the other stuff is basically true in rectangles as well. Okay, property number 9, the determinant of A times B is equal to the determinant of A times the determinant of B. So main example that we've seen so far is like if we factored A into LU. Well, the determinant of A, is equal to the determinant of L times the determinant of U. Which is nice because L and U are upper triangular. Well, upper triangular and lower triangular, they're both triangular. Which means I can just multiply the diagonals of L and U and find their determinants, multiply those together, and that's the determinant of A. So again, if I've already kind of factored it down, remember L has 1s on the diagonal, so the determinant of L will always be 1. U has other things, so really the determinant of A and U are the same here in this particular one. But in general, if I'm multiplying two matrices to get another, I can multiply the determinants to get the determinant of the other two. Okay, and then 10, the determinant of A transpose is the same as the determinant of A. All right, if I switch the rows and the columns, I'll still get AD minus BC with my 2x2 shortcut. What this means, every property that applies to rows also applies to columns. So if you go back through these 10 properties where we said if you have a row of zeros, the determinant is 0. If you have a column of zeros, the determinant will also be 0. If you have 2 rows that are the same, the determinant is 0. If you have 2 columns that are the same, the determinant will also be 0. If I multiply a row by something, it multiplies the determinant by that same thing. If I multiply a column by something, it will multiply the determinant by that same thing. So basically this 10th property says everywhere I see rows in the first 9, columns could be substituted there, and it will do the same. It'll have the same idea. I could do eliminate, like add columns together if I wanted, I guess, and then not change it or whatever. Because the determinant will have the same. It means everything that had rows applied to rows will also apply to columns. All right. So we're just going to do a couple examples of how you could find determinants. With 2x2s, remember, we can always use the shortcut. So determinant of A here would be AD minus BC. If I do elimination, I'm just showing that the determinant of U will be the same. I would take row 2 minus C over A times row 1. All right, that way when I multiply A times C over A, that'll be a minus C, and that'll get rid of that C. So I'll have A and B, and then I'll have C minus C over A times A, which is 0. And then I'll have D minus C over A times B. So the determinant of U, you could do the shortcut, but really this is triangular. So all we have to do is multiply these, which should make sense because if I do the shortcut, it's just the other parts can be 0 anyway. But this is triangular, so I can just multiply the main diagonals. This is A times D minus BC over A, which is AD minus BC. So we see they're the same after doing elimination. Again, just be careful if you put anything here in front of the R2 before doing that. So like we've seen ones where maybe you had a 2 and a 5. And to eliminate the 5, you maybe didn't want to use fractions. So you'd take 2 times row 2 minus 5 times row 1 to do elimination. That's okay, but know that you've now multiplied the determinant by 2. If you wanted the original determinant, this 2 here changed it. Okay, that doubled what your determinant is. So when you get to the end, you'd have to divide by 2 if you wanted the original. So if you ever have to do that, that's okay. You just have to kind of keep track of that or else avoid it when you're doing that. Okay, so here, if I had to find the determinant, I have multiple options. I could do elimination and multiply the pivots. But I see rows that are very similar to rows of a triangular matrix. They're just out of order. So I could switch these rows, for example, and that's just going to give me the same determinant with the opposite signs. Okay, and then I could switch the first 2 rows, and that'll just change the signs again. And now it's lower triangular. All I have to do is multiply the pivots. So I'll have negative, negative 2 times 3 times 3. So a positive 18 is my original determinant. Okay, you could do elimination. You'd get the same thing. Okay, there's going to be a lot of times multiple options on how you could solve this thing. You could transpose it and solve that one. Maybe the transpose would be closer to a triangular matrix or something. So you could do multiple things to get that determinant. Okay, since subtracting multiples of rows from a single row doesn't change the determinant, and exchanging rows will only change the sign, the determinant is the product of the diagonal entries, and the determinant is of a triangular matrix is the product of the diagonal entries. Basically, once I've done elimination, I just multiply the pivots. The only thing that will change the sign, the reason it's plus or minus, is at the beginning you may have switched some rows just to make it easier to start. That's fine. You just have to make sure you pay attention that if I ever switch a row, I keep track of the sign change that'll happen there. And if you ever multiply a row by something, you'd have to keep track of that as well. So just be careful if you ever find that I've multiplied row 2 by 3 to make it easier, or I've multiplied by a half or something, that's changed the determinant, and you need to factor that in as well. So in general, if I don't know what to do, I do elimination. If I don't see an easier path. Like on this first one, that's 0. Okay, I see a row of zeros, it's 0. So I don't really have to do anything else there. On the second one, I don't see any rows that are the same. I don't see any columns that are the same. I don't see anything like super obvious. So then I would just do elimination. So row 2 minus, 2 row 1. And row 3 minus 5 row 1. Shouldn't change the determinant. So I have 0, -1, -2, and then 0, -3, -6. So those two determinants should be the same. And then I could take row 3 minus 3 row 2. And again, that shouldn't change the determinant at all. Now I see a row of zeros, which means this is 0, which means the determinant of the original was 0, which just means the original had some dependent rows. And we can see that because I got a row of zeros. Row of zeros, that tells me I had dependent rows. That tells me the determinant is 0. That tells me there was no inverse. It tells me there's free variables. AX equals 0 has non-zero solutions. Some B's have solutions, some don't. This is where we usually had to find on the last test. Oh, look, a row of zeros. Some B's cannot be solved for. Some things are not consistent there. Okay, so on the homework, when you're looking at determinants, if you see an easy way, like rows of zeros, rows that are the same, columns of zeros, columns that are the same, you can use that. Or if you see one where if I just rearranged some columns or some rows, it would look triangular or something, you can use stuff like that. If you don't, just do elimination. That's going to be kind of your last foolproof way of doing it, is do elimination and multiply the pivots. All right. We still have quite a bit of time if you guys need anything or have any questions. Otherwise, don't forget to turn in your problem set today. And then you guys have a great weekend. And I'll see you guys on Monday.
Can you go over number 6?
Thank you. Have a nice day.